All right, let's dive right into this explainer. We're going to take your grade 11 physical sciences syllabus and past papers and transform them into an absolutely foolproof exam blueprint. If you are looking to truly master mechanics, you are exactly where you need to be. We're taking the exact definitions straight from the Department of Basic Education guidelines and applying them directly to the types of questions that always seem to trip students up the most. Here's what's on the agenda for Term 1. 1. Forces, friction, and free bodies. 2. First law and inertia. 3. Second law and acceleration. 4. Third law, action and reaction. And finally, 5. Universal gravitation and weight. We're setting the rules using the exact DBE guidelines and then testing them out in the arena. So, Section 1, Forces, Friction, and Free Bodies. It's the rulebook versus the arena. Our very first stop is understanding the invisible forces acting on objects, specifically, the tricky differences in friction. This is literally the foundation for everything else we're going to cover. The absolute crucial point from your exam guidelines is the exact wording. Static friction deals with the tendency of motion. Think of it like this. The object isn't moving yet, but it really wants to. Kinetic friction, on the other hand, deals with actual physical movement across a surface. You've got to use these exact terms, tendency of motion versus moving object, because let me tell you, those exam memorandums are incredibly strict about these keywords. Now, what's super interesting is how the Siavula textbook takes this and applies it to the real world. Imagine this scenario. A lady slips in a supermarket, and suddenly you're called in as a science student to testify in court. Your job? Determine if the supermarket floor's static friction actually meets the accepted minimum standard coefficient of 0.5. So it's not just abstract physics anymore, it's physics deciding a real-life legal liability case. How cool is that? To solve that kind of real-world legal problem, the curriculum demands that you methodically break down your investigation into strict, logical steps. You can't just guess, right? You have to explicitly state your investigation question, list every single piece of apparatus, except maybe the tile on the shoe, and then draw a fully labeled diagram to go along with a stepwise method. This structured approach is exactly what examiners are hunting for when they test your practical skills on friction. Moving on to Section 2, First Law and Inertia. The rulebook versus the arena. Let's tackle our first major rule of motion. This really builds our whole understanding of dynamics. Now, listen closely, because you absolutely must memorize this exact wording from the exam guidelines. An object resists changing its state of motion unless acted upon by a non-zero resultant or net force. Essentially, if that net force is zero, the object is either sitting perfectly still or it's just cruising along at a constant velocity. There's literally no in-between. And this law brilliantly explains why your syllabus is so focused on the life-saving importance of seatbelts. You see, inertia is just an object's resistance to a change in motion, and an object's mass is the actual quantitative measure of that inertia. So when a car slams on the brakes rapidly, your body's mass wants to just keep maintaining its constant forward velocity. Without a seatbelt there to apply a net force and stop you, Newton's first law dictates you are just going to keep moving right forward. Let's test this in the arena. If we look at question 1.2 from the November 2025 KZN paper, we see this exact concept in action. The question asks why a passenger standing in a moving bus lurches forward when the bus suddenly stops. Well, like we just talked about, this is a direct textbook application of Newton's first law of motion. The bus gets a net force from the brakes, but the passenger doesn't, so their body simply continues in its state of forward motion. All right, Section 3, Second Law and Acceleration, the rulebook versus the arena. Now we're injecting some acceleration into the mix, and this is where the math really comes alive. The guidelines give us a quote that is the absolute core of dynamics, leading straight to the famous F net equals ma equation. Notice the very specific relationships you need to be able to state. Acceleration is directly proportional to the net force and inversely proportional to the mass. Think of it like this. If you push twice as hard, it accelerates twice as fast. But if it's twice as heavy, it accelerates half as fast. Makes sense, right? Let's jump back into the arena with question 3 from the Eastern Cape past paper. Here we've got a 4,500 kilogram truck towing a 1,250 kilogram bakkie. Now notice how the problem explicitly tells you the truck is traveling at a constant velocity while towing. Guys, this is a massive, massive clue hiding right in plain sight.
The secret to unlocking this kind of tricky two-body problem is realizing that constant velocity means your acceleration is zero. And if acceleration is zero, your net force is zero across the entire system. By drawing a free body diagram for the backy and the truck completely separately, which, by the way, the guidelines strictly advise you to do, you can easily isolate those forces. Because the net force is zero, the forward tension force on the backy absolutely has to perfectly balance the backward kinetic frictional force.
Next up, Section 4. Third law, action and reaction. The rule book versus the arena. This brings us to Newton's third law, which is all about how objects interact with each other. Now, I know this one often trips people up with those action-reaction pairs. The absolute key word from the DBE guidelines here is simultaneously. Forces do not happen in a sequence. They don't take turns. They always exist in pairs at the exact same time. If object A pushes object B is already pushing A with the exact same magnitude, just in the opposite direction. Let's look back at question 1.3 from that same KZN past paper. It asks, if a learner sits on a chair, what is the exact reaction force to her sitting? I know it's incredibly tempting to overthink this. You start wanting to bring in gravity and the earth and the whole shebang. But wait, sticks to the pure definition of object A and object B. If the action is the learner, object A, exerting a downward force on the chair, object B, then the reaction is simply the chair, object B, exerting an upward force on the learner, object A. And that is it. It is not her weight pushing on the earth, and it's certainly not the earth pulling on her. You have to keep it strictly between the two interacting bodies. Finally, Section 5, universal gravitation and weight. The rulebook versus the arena. Let's pull back and look at the biggest force of all, the one literally governing the cosmos. Newton's law of universal gravitation dictates that absolutely everything with mass in the universe is pulling on everything else. The force is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This gives us that classic equation, F equals G times M1 times M2 divided by distance squared. It's the exact reason we stay anchored to the floor right now and the reason the moon stays in orbit around the Earth. Now, the exam guidelines are super strict about making sure you can distinguish between mass and weight. Mass is a scalar quantity measured in kilograms. It's basically how much stuff makes you up, and it never, ever changes, regardless of where you are in the universe. Weight, however, is a vector force, and we measure that in newtons. It's the actual gravitational pull a planet exerts on you. So your mass is constant, but your weight would completely change if you took a quick trip to Mars. Which naturally leads us into this fascinating curriculum concept of weightlessness. What's absolutely crucial to understand here is that weightlessness does not mean gravity has just disappeared. No way. Instead, it happens when an object is in a continuous state of free fall. You're experiencing only the force of gravity, with absolutely no normal force pushing back up against you to give you that sensation of weight. We've unpacked the exact definitions, and we've nailed down the strategies for analyzing these past papers. But I want to leave you with one final provocative thought. If your mass is constant everywhere, but your weight literally vanishes in free fall, what exactly happens to your inertia out in the deep vacuum of space? Keep questioning the forces around you, always trust your free body diagrams, and you are going to completely crush your exams. Thanks for joining me on this explainer.